Thank you. Thank you for showing up this early in the morning. So this is joint work with Lucas, who's here in the audience from Edinburgh, and Higham, who's at Glasgow. I spent quite a bit of time over the last few years looking at what are called adversarial attacks and adversarial algorithms. These are ways of perturbing particular images to cause classifications to change. So I've done quite a lot of work. Some of it's theoretical and some of it's empirical. Today I'm going to focus on the empirical side and maybe say a little bit about some of the theory that exists. So I'll spend some time talking about adversarial attacks for those that aren't familiar with the area. Then I'll join that together with some very recent work we're doing on diffusion models, which is more closely related to what this workshop deals with. This is very recent work, still ongoing, but we have some results which I think will be the end. So adversarial attacks, you've probably heard of AlexNet, which in 2012 completely wiped out the state of the art in image classification, much to the surprise of many experts in the area, using massively parameterized deep learning networks. So here's an example. AlexNet can correctly identify school bus. But very soon after 2012, these papers started to come out on vulnerabilities of these networks. So in the middle there is a set of values for some pixels multiplied by 10 so that we can see them, because otherwise it would be hard to see the values. If you add that pattern to this image, you get the image on the right, which to the human eye looks the same. We haven't really changed the image visually, and yet this very sophisticated prize-winning tool will now identify that as being an ostrich as the most likely category. So we've made a small change to the image, and that's caused a big change to the classification and caused the most probable image category to change. Now, this is not a random perturbation. This is based on partial derivatives. So it's a gradient-based attack. It turns out these are very easy to do. All sophisticated classifiers have this vulnerability built into them, that a tiny change to the image can cause a change in the classification. Why is that the case? Well, one way to think about it is that there are lots of pixels here. If you put them all into a big vector, you're in very high dimension in the input space. So there's lots of different directions, lots of patterns you can choose in which to perturb. So maybe it's not surprising that one of those many directions will be such that the output changes dramatically in that direction. You can also think of concentration of measure. Weird things happen in high dimension. High dimensional L2 unit balls are incredibly difficult to visualize, and randomly sampling or uniformly sampling within a high dimensional unit ball is a very weird thing. Points tend to cluster together, so it's sort of inevitable that a randomly chosen image will be close to some other image with a different category, or will be close to a decision boundary. So concentration of measure is one way of trying to understand why this phenomenon takes place. And this original paper that pointed this out talked about intriguing properties of neural networks. You might think it's a disconcerting or very worrying property of neural networks, depending on your opinion. But there's been lots of work in this area now, coming up with different algorithms to find these attacks and possible defense strategies, either to identify or to guard against such attacks. So there's a cat and mouse game going on that's still continuing. So here's one example of an algorithm that we looked at, just focusing on MNIST, where a simple basic network can quite accurately categorize MNIST digits. So here's an example where we have a digit 7. If you apply the standard L2 attack algorithm called DeepFool, which is built in to PyTorch, then this is the attack that comes out. This is the perturbed image, which is now categorized as an 8 by this network. And Deepfool's trying to find the smallest two-norm perturbation. X is the vector of pixels, and this is the relative change in that vector that's taken place. And maybe it's surprising this is categorized as an 8 because it still looks like a 7. But what we've done with Deepfool is to perturb the background. We've changed those 0 pixels into non-zeros. So we've smudged the background. So Lucas and I looked at some other types of constraint you can put in based on component-wise measures of perturbations. And in particular, if you want to keep the zeros equal to 0, then we can add that in as a constraint. So here's a perturbed digit where we haven't changed the background. We're only perturbing non-zero, so we're changing the ink in the image. And this again is misclassified as an 8. And I think this is a more convincing adversarial attack in the sense that a human would look at that and they might not notice that anything has been done to the image. It just looks as though the ink is a bit less consistent. This does have a bigger two norm. So in the L2 sense, it's a bigger perturbation, but we would argue it's a more useful attack in some circumstances. And if you think of documents with signatures or dates or handwritten checks paying into the bank, this type of phenomenon really is potentially a security issue, in my opinion. These very sophisticated tools will be subject to these types of vulnerabilities. You bury the perturbation inside the ink, and you can still cause these phenomena to take place. We've since looked at other technologies, optical character recognition, using more sophisticated transformer-based architectures. So Lucas wrote out by hand this sentence, which summarizes the first law of robotics. And these systems are incredibly impressive. They've been trained on lots of handwriting. They've been trained on entire sentences and paragraphs. So they have some sense of verbs and nouns and grammar. So they don't just look at each letter one at a time. They have some sense of the context in which they're trying to predict the next word or the next phrase. And this is scanned in and given to the system. It hasn't seen this sentence before, and it correctly interprets that sentence. A robot may not injure a human being. We then do a targeted attack on that scanned image. So here I multiplied the perturbation by 10 just so that we can see it. So we're attacking the ink. This is the perturbed image, and as far as we can see, it's the same input. But when we ask the system to interpret that, we get a robot may now injure a human being. So if you try to interpret the output, you get a very different answer from that. So this is a targeted attack. We wanted to change not into now. We did it by changing many pixels, not just the not to a now, because it's context sensitive. We had to do more of a sophisticated perturbation, but we can do that. So that's the vulnerability of the more sophisticated transformer system. So as I said, there's a lot of research in this area, people doing defense and attack. One of the big names is Carlini, and he recently made the point that in these top tier conferences, you often get authors publishing defense strategies. And then typically within a couple of weeks, someone publishes a way to get around that defense strategy. So the attackers always seem to be one step ahead of the defenders in this world. And I think that's partly because there's these inevitability results that have been proved. It's inevitable that categorizing high-dimensional objects is going to be sensitive in this way. And here's one of the more theoretical papers that gets into that. This is not concentrated measure. Here, they're playing a different game where you give them your neural network and you can have trained it any way you like, and they'll then find a data set. Sorry, you give them your network. You trained it any way you like, give them the network, and they'll find an example where your network is terribly. So they're allowed to find the data, and they'll show that you can get really terrible behavior. So training to zero error will produce something that's unstable in that setting. So you can't have stability and accuracy in the world that they've set up. And just as another digression, we hear a lot these days about regulation. Some very eminent and well-known institutes and people are calling for AI to be regulated. In my opinion, we're being somewhat diverted from some of the bigger picture questions by being warned about AI taking over. And there's this image of robots knocking on the door, telling us that they're now in charge. In my opinion, that's not the problem. I think the problem is that AI doesn't do what it's supposed to do in many cases. So these vulnerabilities, I think, more serious. The problem of AI becoming super powerful is one issue, but the problem of AI not doing what it's supposed to do is another much bigger issue, in my opinion. And there's a nice paper here, came out a few years ago now, more from the social science context, giving lots of examples where AI systems did things which were unintended or inaccurate or caused issues. Lots of case studies where AI didn't do what it was supposed to do. So they came up with this nice phrase, the fallacy of AI functionality. So we're being taught AI is all powerful, and yet in many cases it clearly isn't. Okay, so that's the first half, setting things up. The second half is moving on to diffusion models. We've heard about these quite a bit already this week, but just in case you're not an expert, there's a couple of slides giving you an idea. And if you haven't seen this before, it's very hard to believe it works. We're going to generate, in this case, new digits. And the way we do it is that we learn to denoise completely random starting points. So this is in the training process, we take a training image, we start adding Gaussian noise to each pixel, and by the time we've finished, we've completely eliminated the original information, and we have something that's essentially pure Gaussian independent noise in each pixel, okay? And then we learn to go backwards. So given one of these time points, the neural network is trained to go back and correctly find the image that we started with. So we're solving the heat equation backwards. What a brilliant idea. How could that go wrong? And it does seem to work. So this can be made to succeed in some sense. So that's how the training is done. And then once you have this magic neural network, you can then give it some completely new independent Gaussian noise, and running this backwards process, you can find out which of these images in this world of digits corresponds to that noise. So these are completely new examples which didn't exist in the training data, which arose from, these are 9 independent choices of starting image, and they lead us to these examples. And some of these are somewhat convincing examples of digits. This is just the basic unconditional diffusion model, and it's only on MNIST, but even this is a big computation. You need essentially GPU level computing power just to get these types of models to train and then run. Okay, so that's the basic diffusion process. There's a very well cited paper, and I looked up this morning, I think this is being cited 10 times per day and has been cited 10 times per day since it was published, including weekends. So this is one of the key seminal papers in the area. It built on previous work, of course, but this really put things together in a way that seems to work well. So here's the training algorithm, where we take an image, x0 from the training data, pick a time, add some noise that corresponds to that time, and step 5, we have our neural network, which is now trying to invert that process, trying to give us the image or find the noise which was added corresponding to that time. So that will allow it to take the noise away. So that's training, and then once you've trained, you can start sampling. So take your random capital time t starting point, and then go backwards in time and subtract noise, and what you finish with should look like look like a sample from the space in which you're trying to sample. Okay, so that's the idea. So that gets us to the point of the talk. The question we wanted to address was what happens if you train on adversarial images? So these are very close by to genuine images, but they have a different label according to the classifier. So if you train a diffusion model on adversarial images, will it learn how to generate adversarial examples, or will it just reduce to giving you back images which are correctly classified? So that's the question we wanted to look at. So let's forget about adversarial attacks for the minute. Let's just make sure that we have some reasonable architectures. So we're going to look at MNIST again. We're using a classifier, which is pre-trained. There's the classic LeCun classifier from back in '98. It's reasonably accurate still by today's standards. So LENet is the net we're using to classify a convolutional neural network. When we train a diffusion model, we're using a ResNet architecture. And the initial experiments, nothing adversarial about it. We're just training the diffusion model just to make sure it works and gives things that the classifier thinks look like good images. So we trained in such a way that we now have a somewhat conditional classifier. So when we do the training, we also have the labels included. So this diffusion model is, once it's been trained, you give it a label, and the diffusion model takes a random starting point and tries to generate an image corresponding to that category. Okay, so you give it a label corresponding to 0, and it now tries to generate an image corresponding to that 0 category. Okay, so having set this up, we then tested what the classifier thought about these outputs, and the outputs were correctly classified with around 94.3% accuracy. So we're generating things that look like, according to the classifier, that look like the correct images from the correct category. And just to give you a bit more detail, here's a confusing matrix. So this is what the classifier thought. If we ask the diffusion model, say, for a 0, then for lots of outputs, 98% of the time, the classifier agreed that what was outputted was a 0. So we were getting a good reproduction of examples from the appropriate category. So that's training on correct, clean data. And now I'll give you a result where we train on adversarial data. So here's the setup now. So we have the MNIST data set. We now attack it. So MNIST has 60,000 images. We attack it with a standard L2 adversarial attack algorithm built into PyTorch. This is the reference for PGDL2, projected gradient. Then this algorithm has a default constraint. If it can't find a perturbation within that constraint, it regards the attack as unsuccessful. So it has its own parameter epsilon, and if it can't find an attack within size epsilon, it gives up and says it's failed. Otherwise, it succeeded in changing the category for that image. Okay, so we attacked all the original images, and 52,000 were successfully attacked. So we have a large collection now of adversarial images. That's going to be our training set for the diffusion model. The diffusion model is then given an adversarial image. It's given the original label. So it's given an attacked 0, which has now been recategorized, but it's given the label 0 for that image. That's what we train on. So once we finish the training, we think we've built a model which takes a label, I, and starts with some random image and generates an image which is meant to look like a digit I, but should get misclassified if we're correctly training in an adversarial way. That's what we're hoping to generate. A diffusion model takes a label, generates an image that looks like an I, but is misclassified by the classifier. Okay. So here's a schematic, and these are carefully inserted by Lucas. These really are genuine. So that's a real 3 from MNIST. That's a real attacked 3 by PGDL2. And having trained, this is a real example from the diffusion, which was given the label 3 and outputted this image, which was misclassified by the classifier. Okay, so that's the idea. We built a tool to generate new examples of adversarial images. So I've just got one set of results so far. So here's another pair of confusing matrices. So this is about the L2 attack. This is about the diffusion model that we trained, just allowing you to compare these two different ways of generating adversarial images. So for the L2 attack, this is overall 60,000 original images for a given label. So for label 0, 23% of them were attacked and classified as a 2, and 15% were attacked and classified as a 6. So these are untargeted attacks. 86.5% of the images could be successfully attacked in the sense that the classifier changed its prediction after the attack. So that's the original technology. Here's what happened when we trained the diffusion model and used it to generate images. So if we asked it to generate a 0, then, for example, 23% of the images generated were classified as a 2, 14% classified as a 9, and so on. And overall, 73.4% of the images produced by the diffusion model were misclassified. They didn't agree with the label that we asked it for. Okay, so we are able to produce, at a large scale, examples of adversarial images. And it's possibly interesting just to compare numbers here. So this is a heat map where white is the largest number. So for example, 5 to 3, so taking a 5, changing it to a 3 happened quite a lot. And for the diffusion case, 5 to 3 also happened quite frequently. And there's a reasonable amount of consistency. 1s to 8s was quite high in both cases. But there are some discrepancies as well. You know, some of these ratios don't always match up. So it's somewhat interesting to compare how the diffusion model finds adversarial images relative to how the attack finds different categories. Okay. But roughly speaking, it's doing a similar job in terms of succeeding. Of course, they're very different things. This is taking existing images and trying to change them. And this is just making new images out of random starting points. So these percentages don't really compare in that sense. Okay. And I'll just focus on the 9s now. So if you remember, if we asked the model for a 9, only 4% of the outputs were categorized as a 9. So the rest had different categories. And I'll show you some of the 9s that came out. So again, on the left, we have the traditional gradient attack. So these are the successfully attacked 9s. And here are the 9s that the diffusion model came up with. Some of these are not very convincing. We think we can make this picture better by playing around with the parameters. But there are plenty of quite decent looking 9s in the picture, and only 4% of them on average were classified as 9s. So we are able to produce quite convincing examples of adversarial images. And again, the point is these don't exist in real life. They weren't built by changing real images. They're just built completely out of thin air by starting with random initial points. Okay. So just to wrap up, we think we might call this deceptive diffusion. If you have any other ideas, please tell us. And the idea is to generate examples of adversarial images which didn't previously exist and were not built with traditional gradient-based perturbations. And one of the advantages is that you can generate as many as you like. Once you've built the model, you can just keep generating new examples. So that might be useful in some contexts. It might be useful for attacking, but also in defending. One of the key approaches to defending against attacks is to give, during the training phase, to give the system examples of adversarial images and try to make sure it doesn't get fooled by them. So this will give you a lot more examples to feed in to the training. Also, we'd like to do a more targeted version. So we'd like to have, when we're doing this at the moment, build a model which takes a label I and produces an adversarial image which is categorized with a particular choice of new label J. So those would be targeted adversarial images. That might be useful if you don't have many examples to train on. So this will be a good way of adding to the portfolio of training examples in that targeted scenario. Okay. We'd also like to get around the smudginess. I mean, maybe the diffusion model is just learning how to smudge an image. So we can go back to the adversarial ink algorithm, and we can train on these non-smudged adversarial images. So if we train on lots of these, does the diffusion model learn to produce nice, sharp examples of adversarial images? So that's another test that we hope to do. And we have other ideas for experimental tests, but some of them are top secret, so I can't tell you all the ideas that we have. But there's lots of potential there, I think, for playing around and trying to get some insight into how much you can use diffusion in this adversarial setting. Okay, so thanks for your attention. That's it.
Are there any questions? Yes.
Yeah, general question. Since I train my network in the end for the labeling, I have some type of L2 empirical discretization. And then I ask for pointwise success. I mean, there is already a misconception. So even if I train a lot of adversarial stuff, defense, they put a lot of information, I will still up and maybe more continuous L2 bit, but it will never work in a pointwise setting. But we don't do interpolation and smoothness that helps us. We just are in a regression setup and even empirical. So I'm wondering that the networks, I mean, they will perform maybe better, but in the end, you will always find the X.
Oh, yes. Yeah. So, yeah, I think from the defense point of view, this might help, but it's not going to completely stabilize. And then there are, as I said, there's theory saying you can't possibly build a classifier in high dimension that's stable and accurate. But this is just one possible application for this might be useful adversarial training data.
Yeah, I wonder, I mean, I didn't see it directly, but when I have the opportunity to, for example, have a class of attacks, like you program with this L2 attacks,
Yeah.
and I learn just with a network or with a diffusion model, the kind of attacks, not the resulting, but let's say the difference.
Yeah.
I'm wondering if it's more possible to take a picture and ask a diffusion model, is here some sort of this class of attacks inside?
Yes.
And then you can say, not classify before this, let's say, no, this picture was attacked.
Yes, that's it. Yeah, so that's getting a bit like GANs, you know, which were a big idea 5 years ago. Yeah, this is sort of half a GAN in a way, and you could go back to that kind of idea. Yes, yeah. I mean, also you could look at other. We did L2 here. You could look at all sorts of other. There's L infinity, L1. You know, can a diffusion model learn some better than others? There's all sorts of questions there. Yeah. Yeah.
So if I understand correctly, all of these attacks rely either on having direct access to a model or at least being able to get a lot of samples from
Yes.
the model.
Yes.
Right. So in practice, does that sort of give a case for the not releasing model weights idea?
Yes, that's you can certainly make that argument, but there's also a universality property in two senses. It's been observed empirically that the perturbation that works on one network architecture typically also works on a completely different network architecture.
So it's sort of
Yeah, and it's
something inherent about
Yes.
the data that
But
you
it's-
train it on.
it's, in my opinion, it's something to do with this, everything's linear locally.
Mm.
So, they're all trying to be a linear separator near that point. So it's sort of intuitively reasonable that if they're accurate, they have to do very similar things. And therefore you could train on your own network and use that to find a perturbation that works on a black box. There's also universality across images. The same delta X typically works on different images from the same class, which, again, is not too surprising.
So just having access to whatever an unknown model was trained on. You
Yeah.
train a new model on the same data
Yes.
and hopefully some of the attacks.
Yes. Yeah. There's some universality properties that you can explore.
Do you have any intuition as to why these attacks work? So for example, the ostrich example,
Yeah.
how is it that adding just a small amount of imperceptible noise completely changes the prediction? Because my understanding of like image classification is that the layers kind of go from coarse structures to fine structures, right?
Yeah.
So that the network begins by sort of coarsely classifying an image, and then you're perturbing it at the very fine end of the scales. How do they work? Do you have any sort of intuition?
Well, only I can repeat what I said before. We're in very high dimension, at least in terms of the number of pixels. We're in high dimension. There's lots of different directions there. And one of them might be a direction where the output changes dramatically. From a numerical analysis perspective, what's the condition number? What's the Lipschitz constant? And that's essentially the product of your weight matrices. So if these are big matrices, then that product of matrices can be big. So you certainly can't prove stability through that kind of argument. And there's a concentration of measure. If you have points in very high dimension, it's all very weird. If you're sitting on the North Pole, everything is in the equator. You just can't visualize it in 3D. It doesn't make any sense, but in high dimension, it seems to.
But wouldn't that kind of mean that the picture of the bus that you showed is sitting at a very sort of stable saddle point in the parameter space?
But they're all that bus is not specially chosen. You can do that to any image. Everything's close to a decision boundary.
One last question from Kartik.
A similar question. I was wondering if anyone's looked at first projecting this down into a lower dimension where maybe you can look at things like you mentioned. So instead of doing the classification on the high dimension,